All right, I believe this is the last problem on calculating z-scores. Again, another quick problem. This one says we've got a population of women, and we've measured their heights. And what we found is that the mean is 63.6 inches. And we found that the standard deviation is 2.5 inches. And we want to look at one particular value, 70 inches, and ask what's its z-score and is it unusual, right? First of all, note all those dimensions are in inches. That's one of the real positive features about the standard deviation versus, say, the variance. The standard deviation has the same units as the data values that you're looking at. So again, if we want to calculate z-score, it's just the difference from the mean divided by the standard deviation. So this is x is equal to 70, 63.6 divided by sigma, and I've done that problem and the answer is 2.56. Now, or if I go to B, you know, you might start developing this kind of skill. If this is the mean and this is the standard deviation, go ahead and mentally add those two together. You get 66.1. Do it again, you get 68.6. Yeah, well, 68.6 is less than x. So x is more than 2 standard deviations away. And there you see it, it's more than 2.5. And so the question is it unusual? Yes, unusual. Because it's greater than 2 standard deviations away. So let's get rid of that. And let me just talk briefly about what else you've learned that's consistent with that idea. Let's look at something we're going to look at quite a bit. Let's look at what we've been calling a bell-shaped distribution. We're later going to call this a normal distribution. So this is all the data values. This is how many data values. And if it's a true normal or bell-shaped distribution, it has a maximum in the center, and that maximum is mu. Mu occurs right there, 63.7. And one standard deviation is just 2.5 away from that. This is one standard deviation, 2.5, which makes this number right here 66.1, if I added that correctly. And it makes this number right here, I've got to subtract 2.5, 61.1. And we can continue to do that, but I wanted to draw this so that I could go, hey, here is plus or minus 1 standard deviation. Here is plus or minus 2 standard deviations. Let me do it one more time. This distance right here is plus or minus 3 standard deviations. And the empirical rule says that for a bell-shaped curve, even for an approximately bell-shaped curve, 68% of all the data resides here. 68%. 95% of all the data resides between these two. 95%. And close to nearly all the data, 99.7, occurs here. So you can start to understand why you might choose sigma equals 2 as the sort of demarcation between usual and unusual, because in this regime right here, outside of plus or minus 2 sigma, all that you have left, despite how I've drawn this here, is 5% of the data. You've got 2.5% of the data over here, 2.5% of the data here, 95% of the data there. So if you ask, is a data point that falls out here, anywhere out here, is it unusual? Heck yes. It's less than or equal to 5%. Its value is less than, if you will, 95% of all the other, I'm not saying it the right way. Its value is either greater than or less than 95% of all the data values in that data set. Yeah, you would call that unusual. Okay, we're gonna move on to another topic now.